All right, so continuing on with the chapter 20's problem set answers. All right, so question number 3 here. Turn on the pen, sorry. All right, predict which compound will diffuse across the cell membrane quicker, ethanol or butanol. So in general, for a polar molecule that's already soluble in water, the barrier or the real rate limiting step of it crossing the cell membrane is it dissolving in the nonpolar part of the cell membrane. All right, so in the case of ethanol and butanol, all right, butanol is the more nonpolar of these two molecules. It has 4 carbons, whereas ethanol only has 2. They both have 1 alcohol on them. So butanol is going to be more soluble in the interior of the membrane, so it'll be able to cross the cell membrane more quickly. All right. Question number 4 here. Why is potassium the preferred substrate for the potassium channel compared to sodium? All right, this all has to deal with a part of the protein called the selectivity filter. Now, the selectivity filter basically is going to prefer potassium to sodium. All right, there are really 2 reasons for this. All right, the first one is that it is easier to cleave or easier to remove water. And so it's easier to remove water from potassium. All right, the reason why, well, potassium is a bigger ion, so those bonds are already lengthened more than they would be with sodium. In addition, there are more water molecules around a potassium than there are around a sodium on average. And so as a result, there's more steric repulsion in addition to the longer bond length. So it takes less energy to remove a water off the potassium. So when these ions are going through the channel's not big enough for them and water molecules. So we have to first remove the water molecules from the ions, and we pay a smaller penalty to do that with potassium. All right, so that's our first reason why how this potassium channel prefers potassium to sodium, so we can desolvate potassium easier. All right, the second way is that the carbonyls, so inside of the channel, there are carbonyl groups that are going to form bonds with potassium. And this channel basically has a certain size to it. All right, now the size has basically been evolved to accommodate a large potassium ion. All right, so it can fit potassium in there and form kind of optimal bond lengths with that potassium ion. Now, if instead we put a sodium in there, all right, sodium is a smaller ion. All right, so as a result, these bonds that we are forming now are longer and weaker. All right, so now what does this mean? So with potassium, we have to pay a small uphill energy to desolvate potassium, but then we get out ideal bonds because the carbonyls are the oxygen potassium bonds, are basically short due to the size of that channel. All right, so we end up basically with a net decrease in energy. All right, in the case of sodium, we have to pay a larger penalty to desolvate sodium. In addition, when we come back down and reform bonds, the bonds that we form are less stable bonds than they are for potassium because the sodium isn't able to fill up that space optimally. And so basically there's a larger distance between the sodiums and the oxygen. So we get less energy back out. As a result, sodium binding inside the channel is an energetically uphill process. All right, so that's where I'm going to stop with this particular video.